Welcome to qnawire.
Okay, so we're doing chapter 18, problem 55 here. So this problem says oxygen diffuses from the surface of insects to the interior through tiny tubes called tracheae. An average tracheae is about 2 millimeters long and has a cross-sectional area of 2 times 10 to the negative 9 square meters. Assuming the concentration of oxygen is half what it is outside in the atmosphere, A says show that the concentration of oxygen in the air, assume 21% oxygen at 20 degrees Celsius, 21% at 20 degrees Celsius is 8.7 moles per cubic meter. Okay, so we want to use the ideal gas law first. So if we assume a pressure of 1 atmosphere, then what that means is the pressure caused by the oxygen is the percent of oxygen times the pressure. So this is 21% times P, or 0.21 atmospheres, if we're just talking in terms of oxygen here. So from this, we know that ideal gas law can use this. So let's relate this to N over V, or moles per volume. This is a concentration. So N over V then becomes P over RT. So 0.21 atmospheres times the conversion to SI units times 10 to the 5th pascals per atmosphere. So those will cancel. And then 8.315 times 293 Kelvin. Cool. If we plug that in, we should see this comes out to roughly 8.732 moles per meter cubed, which is exactly what we were trying to show. So awesome, checks out. Part B then. Calculate the diffusion rate, J. Okay, so let's do that. So if we look at equation 1811, it gives us J equaling D times A times the change in concentration with respect to X. And we can approximate this as dA C1 minus C2 over delta X. Cool. So that means the diffusion rate now is given as approximately the diffusion constant here, which is 1 times 10 to the negative 5 square meters per second, times the cross-sectional area, which we have 2 times 10 to the negative 9 square meters. And now let's use the difference in concentrations here. We know that concentration 1 is what we found here, 8.72 moles per cubic meter. And we subtract off half of that because the problem told us that we assume the concentration of oxygen inside is half what it is in the atmosphere. So that's 4.366 moles per meter cubed. And this is all divided by our delta X. And delta X in this case is given as 2 times 10 to the negative 3 meters, because we're looking 2 millimeters along is how long we want to diffuse this oxygen diffuses. Okay, so that should be everything, and we can just plug that in, and this is all in SI units, so we should get an answer that is 4.366 times 10 to the negative 11, and that is moles per second. Awesome. So there's our diffusion rate. And now we move on to part C. Part C says, estimate the average time for a molecule to diffuse in, and assume the diffusion constant is, we already did use that. Okay. So from the example, we know that the time it takes to diffuse is roughly given as the average concentration over the change times delta X squared all over the diffusion constant. Okay, so the average concentration is just the concentration outside plus inside divided by 2. Can times this by delta x, which is 2 times 10 to the negative 3 meters squared, all over delta C now is the difference, which is 8.732 minus 4.366. And we multiply this by our diffusion constant, which is 1 times 10 to the negative 5 meters squared per second. Again, these are all in SI units, so it should come out in seconds. So our calculator says this is 0.6 seconds. So pretty quickly. Awesome.